thank you very much for coming, and thank you for those coming over the internet. It is my great pleasure to introduce research activities of my group. I am privileged to work with excellent postdocs and then hardworking students, and they have produced a lot of interesting research results. So that I want to share with you today. But a little problem is they produce too many interesting results, so I can only introduce selected ones today. And then I also apologize first. I try not go into too much details of the analysis, partly because of the limited amount of time, and partly I don't think it's very interesting unless you're working in the same field. So let me start with first thanking with my team members. Currently I'm working with two postdocs, Songjin and Tae-Jin. Previously I worked with 4 postdocs. Songjin is great. He's taking a responsibility of creating a whole catalog of this AKARI NMP field, which I'll mention later. This is not an easy task, combining 30 different wavelengths with different PSL sizes into one catalog. He's taking care of this important job, and then this catalog will be basis of other people's, all the other people, not just here, but for the entire corporation's research activities. So he's in charge of this important job. And Tae-Jin is also great. He's a paper writing machine. He, in the past 2 years, a little bit more than 2 years, he published 6 papers. And then one is currently submitted to Nature Astronomy, and another one he's almost finished too. So he's very, very productive. One of the I cannot mention all of them, sorry, but one of the paper is featured by British magazine New Scientist. This one I'll talk about later. And also AJ was previous postdoc here, and I will talk about her work about most accurate infrared motion function. Students, I'm really proud of them. They're working hard, and then they published 6 papers, and then they got 21 prizes in total. These are poster prizes, talk prizes, thesis prizes, and many of them got multiple prizes, so I'm really, really proud of them. In terms of paper, there are 6 papers, and then 2 more are submitted recently. So they are really, really working hard. Undergrad students, they are also doing good. They got some poster prizes too, and they also submitted a paper. They are undergrad students, but they are submitted a paper. So I'm really lucky to work with them. And then I'm also working with one high school student at IPSH. She came here for a summer intern student, but she already produced enough results to present at the physics meeting, and this last January, she presented a result in our physics meeting in fact. I have 5 intern students during the summer from Asia, and then one of them submitted a paper. He discovered the most distant supercluster. This work I cannot talk about. I thought this might be worth trying Nature because it's the discovery the most distant supercluster, but he was very humble, so we submitted it to a regular journal. With this wonderful team, we have published many papers. So I have published 40 first author papers with almost 2,000 citations, including co-author papers. I have published 164 papers with 8,000 publications with H-index 45. 5 are press releases, one got paper prize. I believe this is one of the top numbers in my research field. Some papers got a lot of citations. In terms of research grants, it's going well too. So these 3 are basic, most ones, which everybody has, so I don't mention. But I want to emphasize the additional ones. So these are 2-country collaboration projects. I got it Taiwan, Hawaii, Taiwan, Poland, Taiwan, Korea, Taiwan. I will talk about Taiwan, Hawaii later in the talk. Taiwan, Poland, I don't have time to talk about, but these Poland collaborators are experts in machine learning, so there's interesting research going on in this collaboration as well. And then Korea-Taiwan collaboration, I don't have time to talk about, but we are doing a submillimeter survey of NMP field. This is very important data we're taking with Korean people. This is one of the large programs of the JCMT. We also got the MOE grant to improve our classes. I'll talk about in a minute. And then also we got 6 funding to organize AKARI International Conference here at NTHU. I'll talk about this in a minute. This is the summer intern students funding from MOE to have summer intern students. I want to talk about this. So we organized AKARI MEP International Conference in 2018 and 2019. Sonjin worked hard to organize these 2 conferences, and we got 6 grants from PRPC, MOEMOs. We thank them for supporting activity. Each year we had about 50 participants. They look happy here. And I can probably say NTHU is the center of the AKARI MEP field research, because all the international members come here and we do a conference. We have a conference. We got funding for this year too from MOE and MOST, but I'm not sure about it. Because of the coronavirus, maybe, hopefully we can have it later in the year, maybe in November or December. I'm not sure. Now, about this education, so when I arrived at NTHU, I noticed students are not checking archives very often, so that I thought it's not good, because we're doing do research, right? And to do research, it's important to be new or unique. And to be new or unique, you need to know what's happening in the literature. That's very important. So, and this is common practice at major astronomy universities, so we also, NTHU should have it. So we started AstroPH class to check the archive. And at the beginning, people were very few. But now, gradually, students realized or forced me to come, and it started to grow. And now, classrooms are almost full, so I'm happy about that. And this classroom is also funded by MOE this year to improve the class. So some students are working to see what format will be good to try to improve this class. And then here's a question to you. Who have seen this picture this morning? Have you seen this picture this morning? Oh my God, that's great. Okay. So, I'm happy. I am really happy that many NTHU students have seen this. So this is a press release picture from Event Horizon Telescope this morning, or last night or this morning. Then AstroPH is a place to discuss these new results. So if you didn't raise your hand, you're welcome to come to AstroPH today from 12:20 here, and we're going to talk about this result. It's very interesting, it's twisted. Anyway, but I'm really happy many of you raised their hands. So that's good. People are checking papers now. Okay, so this is the index of my research topics that I want to talk about today. First, I'll start with the dark energy. As you probably know, the expansion of the universe is accelerating now. And then this is because of the dark energy. However, this dark energy, we don't know what it is. Okay, if you remember 2011, these people got Nobel Prize by discovering this dark energy. Okay, and then here, I have an apple, right? So what happens if I drop this apple now here? What happens? Karen, what happens? It drops, right? It drops. It drops, right? We all know that. But that's only because we're on Earth. Earth has a strong gravity, right? In vast majority of the space, away from the Earth, away from the Sun, away from stars or black hole, in most of the empty space, if you let the apple go, apple is going to fly away because of the dark energy with the expansion of the universe. This is very mysterious to me, and then we don't know why. We need to figure out why. As a scientist, as a researcher, I believe this is a topic that's worth spending my life on it. That would be very, very interesting topic. In other words, so Newton discovered gravity by watching the falling apple, right? But we have the same opportunity here. Now apple flying away, and then we have a chance, in other words, to make a big discovery like Newton's gravity at this moment now. So we're lucky to be in this era. Okay, let's talk about our research. And then now people have been studying this dark energy. And then now people so if you write down the equation of the state of the dark energy, this W parameter, pressure divided by density, W, and these W's are constant parts. We more or less know this may be close to -1. It's minus because it's repulsing energy, right? It's so it should be minus. So this is near -1. We know that in a plus minus maybe 10% or so. The next key question scientists are focusing on is this time variable part, WZ. So this depends on the redshift Z, right? So this is time variable now. Is this time variable or not? 0 or some number? Is the next big key question, because if it's 0, then it's a cosmological constant, and if it's not, then it's physically different thing. There may be some dynamic fluid, something like that. So 0 or not divides different physics. So it's very important to know this is 0 or not. And that's where people are spending billions of dollars to do a big project to figure this out. And then we had a new idea how to measure this. Okay, let's look at the current state of the art. So this, okay, W0 parameter. This is the first constant part. We sort of know, more and more know it's -1 plus minus 10% or so. So we have more and more knowledge of this. But this time variable part, WZ, we have no idea. It's error bar is so large, right? It may be 0, it may be plus 0.5 or minus 0.5. We have less idea. So this is the next target for us. Okay. Then to prove the time variability of dark energy, because this is a variability, we need to investigate a long time span. In other words, we need to go to high redshift. In this figure, we need to study high redshift. As you can see, so these numbers are different dark energy models, and as you can see, the model difference of the models are larger here, because if it's time variable, long time scale, the difference will be larger, right? So this is our target. We need to investigate here. These gray points are supernova, then nearby universe. So here, supernova unfortunately stops at 1.5 or so. Because supernovas are bright, minus 90 magnitude, but that's not quite bright enough at high Z, redshift 2 and above, for example. It becomes too faint, and especially to do spectroscopy to classify the types of supernova will be very difficult at redshift 2 and above. Now, more fundamentally, type 1 supernova are white dwarf binary, so it needs some time to accrete mass from the companion before exploding, before reaching a Chandrasekhar mass and exploding. And it takes few gigayears. That means when the age of the universe is less than few gigayears, there will be no type 1 supernova. This is fundamental problem. We cannot use type 1 supernova to probe higher redshift. So we need a brighter standard candle. What we focused on is fast radio burst. This is another mysterious object. Fast radio burst is a millisecond burst in radio. So all of the sudden there's a burst of radio flux, and a millisecond, you see these are milliseconds. So see this like 8 milliseconds, one axis. So very short burst. And then it's very bright, Jansky level, so our telescopes can easily detect it. And then brief millisecond, and it's transient, it disappears, right? And it quickly disappears. Only 100 so are discovered so far. And then we don't know what it is. Presenting the unknown, another mystery is here. And if you extrapolate to the whole sky, there are 5,000 on the sky every day, so there are plenty of them. But we know these are extragalactic because you see here, this Persian measure, the burst is shifting as a function of frequency, right? That means it has been traveling through the large space of the plasma. So this cannot be in the Milky Way. This is extragalactic. That's what we know. And then explosion of discovery is happening now. So this is This is number of first rate. This is not the coronavirus patient's number. this is FRB number per year. And this is a year, right? Now it's 2018. The number, we had very few before. But recently it's exploding, more and more discovered because there are those telescopes started to work operating or started to look for these. So now is the time to, now this is a very hot topic in astronomy. Okay, then what we found, this is called, this is Tetsuya's paper, is the correlation between the duration of the burst, how many milliseconds this is going to last, and then the radioluminosity. We found a correlation here. I know you say scatter is large, but the correlation coefficient is very, Pearson's p-value is very small, so this is weak but very significant correlation. And this is this paper, Tetsuya's paper. Why this correlation is important? There are many important points about this correlation, but I only focus on one. One is we can test the variability of dark energy using this relation. Here's how it works. So this duration of the burst, how many milliseconds, we can measure from the observation. You do point array the telescope, found it, okay, how many milliseconds, we can measure. We measure, and we use this Tetsuya's relation, and then you go here, read it off, and then you get the luminosity, radial luminosity, without using redshift. And then if you know the luminosity, by comparing the luminosity to observe the flux, you know the luminosity distance, right? So you will know the distances to all of the radial bursts if you use this relation. Then if you know the distances, then you can test the expansion of the universe, how fast it is, right? So that's why this relation is very, very interesting. And then also British magazine, New Scientist, thought it's an interesting idea, so the paper is featured in his magazine. Okay. And then, I should mention this. First radial bursts are bright, so we can go much farther distance than the supernova. Okay, and then also did the simulation for the future. Okay, so this is simulation for the future. In the near future, square kilometer array, SK, this is a very big radio telescope. Here is going to find thousands of first radio bursts with spectroscopic redshift. And if you assume this SK accuracy, then we can constrain the time variability of the dark energy to the 10% level. This is fulfilling one of the goals of the dark energy task force. So that's why this paper, I think, is very interesting. We also have some implications for the origin of this mysterious first radio burst. As I mentioned, nobody knows what this object is. And then Tetsuya, this is another Tetsuya's paper, and then he measured the luminosity function of FRBs as a function of redshift. So here is the number density of FRB, and this is luminosity, and so per luminosity, what's the number density as a function of redshift. So blue, green, red is going to low redshift, mid redshift, high redshift. And if you assume that the slope, it seems it's evolving towards higher redshift. Oh, I should have mentioned there are two types of FRB. The repeating one is the same position. The burst happens many times, multiple times, and a non-repeating one, but only one burst. So there are two types. And then non-repeating one also made a luminosity function. Then non-repeating one from low redshift blue to red, it seems they are on top of each other, so there's not much evolution. This is very interesting in two ways. The first one is repeating and non-repeating looks like very different properties. Maybe they are different origin, perhaps. And it's more interesting if you plot it this way. So this is number density of FRB as a function of look-back time or redshift. So this is further back in the universe. And this is for repeating FRBs. And repeating FRB are increasing, right, towards the past. They'll pass more repeating FRBs. And then this blue one is star formation, cosmic star formation history. And the red one is cosmic stellar mass density evolution history. Which one does it agree with? The blue one, right? So the blue one, and the blue one is this star formation history. So these are caused by young stars, OB stars. And then FRB's evolution is almost tracing that. So repeating FRB may be from this young population of stars. And this is the first time we have evidence on the origin of the FRB. This is very exciting. And then for non-repeating one, this is one time burst only. So these are red points are non-repeating FRB as a function relative to again. Which one does it agree this time? It's orange one, right? And orange one are old stars, like the sun, FGM, so those old stars. So maybe non-repeating one is coming from old star populations. And this is the first time we got this kind of evidence. So NTHU submitted it to, okay, this is not science, Nature Astronomy NTHU submitted. So it'll be interesting to hear back from them. Okay, let's move on to the dark side of the cosmic star formation history. So this is a AKARI Space Telescope project. That's our space telescope, and this summary of these three papers on itself. Okay, scientific motivation here is in the 13 billion years of history of the universe, when and how much stars are made by the universe. We want to reveal this cosmic star formation history. This is one of the big topics in astronomy. Thousands of astronomers are still working on this topic. And many people are working using a UV or optical telescope on the ground. But then if you're using UV optical telescope on Earth, there's a problem. You suffer from dust extinction. So you only can measure the lower limit. And you don't know how much star formation is obscured by dust. So there might be there's a dark side of the cosmic star formation history. We want to reveal here how much star formation is hidden by the dust. And how do we do that? Because the star forming regions emit strong UV light, right? But then it's obscured by the dust. That's a problem. So we cannot see in UV optical. But this light absorbed by dust is re-emitted in infrared. So if we build and launch infrared space telescope, we can observe infrared part, then we can reveal the hidden part of the star formation history. That's why we built this AKARI Space Infrared Telescope. Of course, mid and far infrared telescope need to be in space because you cannot observe from the ground. So it's a space telescope, and then we launched it. So it's up in space, and then it was on sun-synchronous orbit, and it was observing like this. For space telescope, the enemy is the sun and Earth. This comes back later, so please remember. The sun and Earth telescope don't want to observe, right? Okay, so it was observing away from the sun and Earth. And then so it was doing all skies. It did the two major surveys, whole sky survey, like this, stripe by stripe. And then for this NAP region, North Ecliptic Pole region, it can observe in every orbit. So we have a deep field here. First, I'll talk about the result from this deep field. So this is the AKARI NAP deep field data. This is mid-infrared data. And a very unique feature of AKARI telescope in this region is it has continuous 9 filters in mid-infrared. There's no gap. For example, NASA's Spitzer Space Telescope. It was a great telescope, but it had a gap from 8 micron, between 8 micron and 24 micron here. So if your feature is here, there's nothing to do. And then this was a big problem for the Spitzer telescope. This was creating largest uncertainty for Spitzer telescope-based research papers. And then we can remove this uncertainty because we have filters here. So that's the unique feature of the AKARI telescope. However, we also had a problem. So this is the AKARI's mid-infrared data. It spans very large field, 5 square degrees. This actually put up by Sunjin's hard work on this. But we only had optical data in this tiny field. But we need optical data to measure photometric redshift of these sources. Without photometric redshift, those infrared sources are precious, but we don't know the distance, so we don't know the luminosity, so we cannot do science with them. So all our previous papers are based on this tiny area, while precious space telescope data exists more. But we recently fixed this problem using this Subaru telescope, new hyper-sprang. It's a new big camera on Subaru 8-meter telescope. This is 3 tons. It's a little bigger than me, and then it's on top of the Subaru telescope. Subaru telescope is the only stiff telescope to have such a gigantic camera on the prime focus. So we use this camera and then observe this AKARI's NEB region. We only need 4 pointings to cover the entire region. So the area became 20 times larger, and then, now we can use the whole AKARI NEB's space telescope data to do science. So I won't talk about analysis detail, but AKARI's infrared sources, they are free from dust extinction, and then we now have photometric redshift from Subaru telescope data. So now by combining these two, we can reveal the dust hidden part of the cosmic star formation history. And here's the result. So that's my recent paper. So as a function of redshift, the star formation density of the universe is almost 10 times larger by redshift 1. The key point here, this is free because we're using infrared. It's free from the dust extinction, and then we have more filters than Spitzer, so it's more accurate than the NASA Spitzer result. And then this is one of the key results from the AKARI Space Telescope project. Okay. Next, I want to introduce another paper that we wrote from the alsky survey of AKARI with my former postdoc AJ. She was here until 2 years ago. So now, in a lot of future space telescopes, including NASA's JWST 30-meter telescope and European's extremely large telescope, these are focusing on pushing this cosmic star formation history to more farther and farther in the past. So, gigantic telescope, faint galaxies, push it higher and higher redshift. But what we want to investigate is evolution. We want to investigate the difference between low redshift and high redshift. So I believe it is equally important to have a very accurate data point at low redshift. And that's when our AKARI telescope's alsky survey can do a very good job. So in this field, there was a seminal paper by this David Sanders. Everybody cites his paper for low redshift benchmark. So this paper was cited more than 1,000 times. But he was using data from IRIS satellite, which is 20 years ago. So AKARI can do much better job in these 2 points, which I mentioned now. One is availability of 160 micron filter. So this is the ACD fitting to individual galaxies in infrared part. And IRIS had only data point up to 100 micron. If your data point is limited to 100 micron, you never know if ACDs continue to rise up or ACD is going to turn around. And then this is going to create a big uncertainty in measuring the infrared velocity of galaxies. In contrast, AKARI has those additional 2 data points, 140 micron and 160 micron. If you have 160 micron, you can capture the peak of the dust luminosity. So we know, okay, it's turning around. And then this way you can measure the infrared luminosity much more accurately. And in fact, this having one data point beyond peak is critical in measuring the infrared luminosity of individual galaxies. And then AKARI is the only satellite to provide 160 micron for the whole sky. The other point is this Sanders paper only used 600 galaxies. But we, AJ and I, combine AKARI data with multiple redshift surveys and then we collected 15,000 galaxies. That's 20 times larger sample than David Sanders. So we are better than David Sanders' seminal paper in these 2 points, and then we have put this is the data point we measured. This is, I believe, is the best data point in optical redshift. And I want to emphasize, no future far-infrared all-sky survey mission is planned. AKARI is, at the moment, the last all-sky survey mission in far-infrared. So our result will be the best data point for at least next decades, I believe. This kind of research is not so sexy. It's too sexy to build a big telescope and push it high redshift. That's attractive, right? This is nearby universe, so it may not be so attractive, but scientifically, I think this kind of research is very important to make use of all the results from the big telescopes.
So Tomo,
yes?
how do you compare AKARI with Herschel?
Herschel is by infrared. AKARI is mid-infrared.
It's like overlap quite a lot.
So both AKARI and Herschel can do this. But for example, low redshift all-sky survey, only AKARI can do it because Herschel didn't do the all-sky survey. Okay, so let's go to the dark age next time. 100 supermassive black holes. So dark age of the universe. So in our current understanding of the universe, after the Big Bang, universe expanded, and then with expansion, universe cooled down, and universe became neutral. But if you look at up the sky now, universe is ionized. So universe was re-ionized from neutral to ionized in a very early age. And that is called cosmic reionization, and that's indicating the end of the dark age of the universe. So this is a simulation of the cosmic reionization. So neutral universe after the Big Bang is not ionized now, but it will be, okay. It's gradually ionized and becomes transparent. If you're neutral, the light cannot go out, right? So it's dark age. But now gradually ionized and the universe becomes transparent. But this is only simulation, and observationally, we haven't observed this. We haven't figured this out. So to observationally figure this out is one of the big goals in this field. One of the direct way to do this is to use very distant quasar as a background source. Here's how it works. You find a very distant quasar, and then light travels to us, over here. And then when the quasar's light goes through neutral part of the universe, the light is absorbed. So there's a shadow in the quasar spectrum. But if the quasar light is going through ionized part of the universe, there's a remaining flux in the spectrum. So in other words, first find very distant quasar, take deep spectrum, then cosmic reionization history is imprinted here. So that's how it works. And then of course, to do this, we want a bright quasar and very distant one, preferably going into the dark age of the universe at left 6 and 7. Okay, so this is dark part of the universe, and we want to, because this background light, we want very farther away, more distant quasar than the dark age. But it's a very difficult task because quasars are very rare. Quasars are only one out of 100 billion objects. So it's very difficult to find this. It's more difficult statistically than finding a needle in a haystack because there's no 100 billion haze in here, right? So that's the task we are facing. And to achieve this, we are performing Subaru Hyperspectrum Count 309 survey. This is a big survey using again this huge large new camera on top of the 8 meter Subaru telescope. We're using 309 and then surveying 1400 square degrees. And this is the first over 1000 square degrees survey with an 8 meter telescope there. So we detect faint objects because our telescope is big over 1400 square degrees. So, okay. The reason we can do this is because this new Subaru's new camera's field of view is very large. So this is Hyperspectrum Count field of view, cyan. Compared to Hubble, Hubble's field of view is invisible. And this is Subaru from its previous Subaru's camera, which was the largest among 8-meter telescope, but even compared to previous largest one, hyperspancum is 10 times larger. So that's why we can survey large area in a quick amount, reasonable amount of time. How do we find redshift 6 and 7 quasars? I don't go into the detail, but the essence is here. With the red expansion, with the redshift, the high redshift objects become redder and redder, right? So in this color plot, for example, G minus Y color, quasars become redder and redder and redder as it goes far away, as it goes higher redshift. So in simple words, we're looking for very red objects in our huge data from hyperspancum. Here's the result. We have found 100 new quasars. So each one of these red dots at the center are very distant quasars, redshift 6 and 7. And since finding 100, previously only something like 20 are known, by finding 100 at distant universe was one milestone. So we did a press release, and then it was featured in Taiwan's newspaper and also NTHU website as well. If you remember, yes.
Is there any reason why they sit at the center of the square? Previous photo.
Previous photo.
Yeah.
This one.
They all sit in the center of the square. Why so?
Because we arranged it that way. We cut out the image around the center of the.
Oh, so this is not just one.
These are
put the image together.
That's right. Put it together. Cut it out this square region and then put it together. So. Okay. If you remember, during my last promotion talk, I predicted this. So this slide from my last promotion talk, and I was hoping that we might find the most distant quasar like this. This is all our physics department website. We didn't find the most distant one, but we found 101, and then was lucky picked up on the NTHU website. And here, even kindergarten children are interested in black holes. Okay, so we are scientists. We are not doing this to find more than 100, 200. We are not doing this just to find quasars, right? We're not find very rare object, I'm happy. No, we are not like that. We are scientists. We are trying to learn physics from them. And then what we learned is, so these 100 quasars is just for press. It's not scientifically important. The scientifically important thing is we found those quasars did not reionize the universe. Here's what that's. So this is luminosity function of quasar as a function of brightness. This is number density, and our data points are this big one. And then so I talk about cosmic reionization. It's another important question: which object reionize the universe? Is it a black hole or stars or galaxies? And then some people claim that it might be black hole. Black holes UV light ionize the universe. But our answer is no, because to ionize the universe, we need this much quasar, 10 to the 4. But we found is up to here, at most 10 to the 2 per cubic gigaparsec. So that's not enough quasar to reionize the universe. So we ruled out quasar as a reionization source of the universe. That's scientifically important discovery of this. In other words, we found 100 quasars, but we only found 100 quasars. To be able to ionize the universe, we should have found 10,000 quasars in our survey, but we didn't. We only found 100. So that's too few. That's the scientifically important results of this research. I have one more interesting result from the same hyperspancum Subaru 309 survey. That is a discovery of the most distant protocluster of redshift 6.6. So this is a protocluster. So these galaxies are clustered in a tiny region of several megaparsec at redshift 6.6. And this is a new record in finding such a protocluster. So that was also picked up by the newspaper. Okay, then Tesla also found this is another one of the Tesla's paper, is very unusually blue cluster in a low redshift universe. Maybe it's better to show this. This is nearby galaxy cluster. A nearby galaxy cluster is usually filled with red and dead galaxies. But this cluster, more than half of the galaxies are blue star-forming galaxies. That is unexpected in around the CTM simulation. So this is interesting discovery. This may be something similar to the protocluster we find at high redshift universe. If you look at this, well, see, this is, let me explain this a little bit. So this is a fraction of blue galaxies over the entire galaxies in a galaxy cluster. Then most of the galaxies are here. Only 20% of the galaxies are blue, right? But this cluster, 60% of the galaxies are blue. This is for sigma outlier, and it's unexpected in a lambda CDO simulation. Okay. Also, from here, I want to introduce ongoing or future research. There are some exciting research are going on in our group. The first one of my students is trying to measure cosmic reionization using this 100 quasars we found. So this is the plot. So as a function of redshift, she's plotting optical depth. So this is optical depth. So large number means neutral. Small number is ionized universe. And as you see, we go higher redshift, universe becomes more and more neutral, right? Going into dark age of the universe. And our data points are here, red ones. So we are pushing it to higher and higher redshift to the frontier of this research. I think I hope she's preparing a paper draft now. I think. This is another ongoing work by another student. So by stacking, to study the host galaxies of these 100 quasars. These host galaxies at redshift 6 and 7 are very faint. So usually you cannot detect it. But because we have 100 of them, he stacked 100 of them together. And then that's not enough. In addition, the further difficulty is for these quasars. So in the center, there's a bright quasar. So you need to subtract this light carefully to see the faint host galaxy around it. And he did it. So this is the 100 quasar stack. And then this is a point spread function, basically stars stack. And then this minus this, and then you see extended structure. These are host galaxies. First time seen at redshift 6 and 7. This is a very exciting result too, I think. In the AKARI field, our future is very bright here too. So I mentioned this sun synchronous orbit. The deep field, AKARI deep field is here because space telescopes do not want to look at the sun or the Earth. It's the same for other future telescopes. So all these future gigantic telescopes have a deep field in our NEP field, including JWST, Euclid telescope, and then Russia's Rosita X-ray telescope. They all have deep fields in NEP. They are following our direction. And then we already have AKARI data and deep HSC data in that region. And then in addition, we have more data that Sonjin is combining. So we have advantage in this NEP field, and then we want to read this exciting research in the NEP research field. So as soon as those gigantic telescopes produce data, we can do science. We have photometric research, we are ready to do that. One of the attempts, we are collaborating with Dave Sanders at the University of Hawaii to take more HSC data in this NEP field. This is our field, and we are taking more data. And also, in collaboration with him, we spent 1 year of Spitzer time, 1 year of space telescope time to observe this region much deeper. So we're ready, we're waiting for these future JWST to go up and then observe our field, if I say. We're waiting. One example is JWST. So this is going to revolutionize the astronomy because this is almost 3 times larger than Hubble, right? And the space telescope, NASA's next billion project. And it's going out in next, it's going to space launched in next year. And if you look at this database is mid-infrared filter. So this is 5 micron to 30 micron. These are database teeth filters. And these are very similar to AKARI's, our telescope's mid-infrared filters. And then my students, Tina and Da, are already trained to deal with this mid-infrared data. They actually are writing paper how to select dust obscured black holes again from this mid-infrared data. And then Tina already submitted a paper, and they already know the technique and code to do that. So as soon as database data becomes available, they are going to analyze data and then produce first result from the database. That's our plan. I'm excited about it. Lastly, another famous student is working. Did you know that there is another planet in this solar system? Did you know that? Outside of Neptune. I'm not talking about Pluto. Pluto is the planet. There's another gigantic planet like Neptune there is in our solar system. 90% of the researchers working in this field, we believe it. The reason is here. So here's the sun. And then these days, these small, because the telescope bigger and bigger, these small Kuiper objects are being found. And some of the examples here, these are very distant Kuiper objects. But these are only one side of the solar system. There's no Kuiper object here. Why? That's because there's a gigantic planet 9 here, and then kicking those small bodies from this side. Small bodies can only survive on this side. And then, this is not very good figure, but there's a gap here on the distribution of Kuiper object, and exactly expected at the expected orbit of this planet 9. And this gap is more stronger evidence of the planet 9. This is like, for example, saying you go to Taipei station and you see many people, right? And all the people are looking at the same direction. Does that happen by chance? It doesn't, right? But it's happening here. So there should be a reason. And then most natural reason is, researchers compared with many theories. For example, maybe these are droplets, group of dwarf planet, small object came into the solar system by chance or something. So that may be one, but that's more unlikely. So the most likely, most reasonable explanation for this is gigantic planet. But the problem is this planet 9 is very difficult to find because this is very faint in optical. This is about 700 AU. So Neptune is 40 AU or something, right? So it's 20 times far away. So it's very faint in optical. So it's very difficult to find it. So how do we find it? These are low temperature body, right? Because this is a planet, so it's low temperature. Low temperature objects are brighter in what wavelengths? Infrared, right? Because low temperature, infrared. And then we have the infrared telescope, which did the whole sky survey. As he calculated, as the cosmos calculated, it's easily detectable. It's very difficult to detect in optical, but with the largest telescope. But in infrared, it's very, very bright. So it should be in our data, in this infrared telescope. So now this famous student is searching for this kind of object. For example, this is one of the candidates. So this was detected, this object was detected with IRIS. This is a previous infrared satellite in 1980s, but not with AKARI in 2000, 20 years later. So in IRIS, 20 years ago it was here. And there's one object here, so 20 years later it's here. So maybe it has moved. So this is one of the candidates of this planet. So this student is famous student because he's the first one who got quarantined, right? But he was negative. He was negative. So I knew he was negative because look at this. He was already sick before going to Japan's winter school. So I thought I knew he was sick already in Taiwan. I thought he was negative. Okay, so here's the topics I talked about today. I won't repeat it again. Instead, I again show you the prediction. So maybe in 2020 something, if he's worked good enough, maybe we can put another student found the Plan X on NTHU website. I hope this happens. Okay, I stop here. Thank you very much for everyone. Thank you very much.